Thank you. All right, rotated conics. Now, as I previewed yesterday, sorry, Daryl, you missed that. We have a fairly set technique for this. It'll look a little bit different on the helpful sheet I'm going to give you at the end today with some hints on it. But if you're looking at a general form of a conic, you know this is the general form of a conic. You see ax squared minus bxy plus cy squared. D is equal to 0, E is equal to 0, F is equal to 16. So this is the general form we've been talking about before. If you see an xy term, you are looking at a conic that has been rotated. It might have been rotated 90 degrees, and you never know. It might actually line up with the axes again, but you don't know that looking at this. You also can't use your tricks for identifying the conic. Normally, if you see 7x squared plus 13y squared, you would say this is an ellipse, because I have an x squared term, a y squared term, and they're different numbers, so it's not a circle. But that trick doesn't particularly work here. They can change signs, they can change numbers. How much has it been rotated? The formula I gave you yesterday was tangent 2 theta equals b over a minus c. Incidentally, the sheet I'm going to give you for some reason from another publisher actually says cotangent 2 theta equals a minus c over b, but they're reciprocal, so I should be able to handle that. Now for this one, this leads to negative 6 root 3, let me keep track of that, divided by 7 minus 13. Did I plug in my b and my a and my c correctly?
Yeah.
Yeah.
Excellent. So that is negative 6 root 3 divided by negative 6, or positive root 3. Here's where your intense knowledge of the unit circle comes in. And the rotations you're going to get without a calculator are only 30, 45, and 16. I don't think I'm going to let you use a unit circle on this one. So what is this?
Alright, so one cosine, and one of the cosines is root 3 over 2, and the sine will, well, wait, is sine over...
Michelle, jump to the thrilling conclusion. 60 degrees. Yes, you're right. You're going to have sine root 3 over 2 over, you're remembering it as root 3 over 2 over 1/2, correct?
Right.
So what angle has a sine of root 3 over 2 and a cosine of 1/2, since tangent is sine over cosine? But Michelle beat you to it. This tells me that if the tangent of 2 theta is root 3, then 2 theta is 60 degrees. Very good.
So theta is...
Bingo. So theta is 30 degrees. We're sticking to quadrant 1 for this unit. You can rotate these things further than 90 degrees. You can rotate them as many times around as you want, but I'm not going to make you, without a calculator or a computer program, figure out rotations beyond 0 to 90.
Does that would be clockwise though with our
No.
or is that?
Go this way. Like you don't even.
This way, a little bit differently from what we do with parametrics, and since I switched publishers, it's a little bit different what I previewed yesterday. This is actually going to be, we're back in, this book uses the formulas we're going to use. We're back in Cartesian land. This has been rotated 30 degrees up from the x-axis.
Is this a class that's already started?
And it's recording for the internet, so, yeah. Okay, so, alright, so this one is, yeah, this has been rotated up 30 degrees from the x-axis. We're going to go back to that orientation. Now, so I think it's a little different from what I told you yesterday, but the formulas that will get us back to where we started, I'm going to lose the prime notation, which will still be in the books. And I'm just going to tell you, for purposes of just me being able to grade your work with it being somewhat neatly, I've done more neatly, just take the x's and replace them with x cosine theta minus y sine theta. Take the y's and replace them with x sine theta plus y cosine theta. You're going to have to know this for the test. You have to have these memorized. My way of remembering them was always x equals x cosine, and cosine always goes with x. Y equals x sine, sine always goes with y. The minus before plus, I don't have a clever mnemonic for it. But for the x's, it lines up intuitively, but it's negative. The x with the cosine, the y with the sine. For the y's, the x's, the sine, and the cosine don't line up with the things they normally line up with, but it's positive. Daryl, you missed this yesterday. What we're going to do now is, in this equation, everywhere we see an x, we're going to substitute it with this. And in this original equation, everywhere we see a y, we're going to substitute it with this, with theta being 30 degrees. What this does is it takes this rotated conic and it re-rotates it back. Okay, so we see what shape this would be if it weren't rotated 30 degrees. And we're going to graph it at that 30-degree angle. So we're going to put it back first. If we successfully unrotate it, bring it back to what it would look like if it weren't rotated, this term must disappear. But these terms are going to change so much that it's really hard to predict what this will be first. At least not at a glance, like you can if it's not rotated. Okay, you guys ready? There's absolutely no new algebra in this, but nothing you haven't done before. But it's going to be a lot of it. Okay, so 7x squared is going to become 7 times, first let's fill in these details. Well, first, x cosine theta, I'll just show you step up here. X cosine theta minus y sine theta squared minus 6 root 3 x cosine theta minus sine theta times x sine theta minus y cosine theta.
Wait, Mr. Bella, why
Yeah.
did you get minus y sine theta?
Because it should be plus, and I'm trusting you guys to keep
Okay,
me.
and also for that one, it should be a y.
I wish I could say that was intentional on my part to show you guys just how easy it is to mess up the details on this, but Michelle, I'm glad you caught that.
If we mess it up, it changes everything, right?
Oh, it's hopeless, yeah. But 13, I'm replacing that with the x sine theta plus y cosine theta squared minus 16 equals 0. What I should have done over there is plugged in the values for these first, but I'll do that now in my next step. What's the cosine of 30 degrees?
Cosine is
Root 3 over 2. So this becomes root 3 over 2x minus sine of 30 degrees, Joey?
1/2.
There you go. Minus 1/2 y squared. Minus 6 root 3. Cosine again, root 3 over 2x minus 1/2 y times sine of 30, 1/2 x plus root 3 over 2y plus 13, 1/2 x plus root 3 over 2y squared minus 16 equals 0. Now we got a whole lot of foiling going on.
Wait, so can we take, like, the middle terms by taking out, like, to get rid of the square root, we can cross it like 1/2 x plus root 3 squared y. No?
No, just have to foil.
Okay.
Can't factor anything out, can't get rid of the square root. We can distribute in a minute. Always, in my opinion, smarter to foil before distributing. Also makes it much easier to double check. You really want to be neat and show every step on this one. There's pretty much no way around that.
It seemed like they take like such a long time.
Well, factoring patterns help. I'm glad you said that. Because if you remember that a minus b squared is a squared minus 2ab plus b squared. That's faster for the foiling. And if you remember that a plus b, quantity squared, is a squared plus 2ab plus b squared. you'll save yourself some time. Not so much here in May. So with that in mind, this becomes 7a squared. Becomes, let's see, root 3 over 2 squared becomes 3/4, and x squared is x squared. 2ab, okay. Root 3 over 2x times 1/2 y would be root 3 over 4xy. That always gets doubled in this pattern. So that's root 3 over 2xy. It's what you should get if you FOIL it. Multiply these together, double them. B squared plus 1/4 y squared.
I think I'm gonna like probably mess
Yeah, but you'll triple check it, so I'm not too worried about it. This one I've just got to FOIL. Personally, some people see shortcuts better than I do. Root
3
3,
over 4x squared.
very good. Outer?
Root negative root 3 over 4. Wait,
No,
Outer?
just did it. It's
3 over 4xy.
3/4 xy. Inner?
That's 1/4.
Minus 1/4 xy, very good. Last?
And that is negative root 3 over 4.
Y squared. Very good. Plus 13, a plus b squared. 1/4 x squared plus, multiply these together, root 3 over 4, double that, root 3 over 2 xy. B squared plus 3/4 y squared minus 16 equals 0. Yeah, when I'm foiling, I always actually go, this is the one case where I always make sure I go first, outer, inner, last, and write everything out. Because if these xy terms don't disappear in a few steps, we have to go back and figure out why not. And the less you've written down and the less carefully you've written down that information, the longer that's going to take. There's a couple things we can do from here. We can distribute first. Some of it depends on your comfort level with fractions. If you multiply everything by 4, you could leapfrog over the 7, the 6 root 3, and the 13 and get rid of all of your fractions. So you have to make sure you multiply the 16 by 4 at the end as well. Will that make it easier? I don't know. Depends more on you. Or we can distribute without getting rid of the fractions and just keep careful track of our denominators.
Wait, can we get rid of the fractions?
You like that idea? Yes.
Wait a minute. If root 3 over 2 times negative 1/2, wouldn't it be negative root 3 over 4?
Yes. And then it gets, are you talking about here and here?
Yeah.
But it gets doubled.
Oh.
When you're squaring a binomial, that term occurs twice.
Okay.
So that's why it's minus 2ab or plus 2ab.
Okay.
And double root 3 over 4 should be root 3 over 2. But please ask me and double check me, because I will mess something up. Michelle has a vote for getting rid of the fractions. Okay, anyone object?
I just do
I
simple distributing.
First? Okay.
Fewer steps.
Let's try this. It is fewer steps, but if we get rid of all the fractions, we can ignore the 7, just multiply everything by 4 over it, and we'll get 3x squared minus 2 root 3xy, very good, Daryl, plus y squared, continuing to multiply by 4, ignoring the 6 root 3, yep, and then
Minus xy minus, no,
just root 3, I think.
y
Oh, wait,
squared.
why do I have a 2?
If I've done this right, feel free to double check.
No, you're right, I just wrote the wrong number.
Plus 13,
Plus 13,
just x squared,
2 root 3xy plus 3y squared. Yeah.
and then minus how much?
Minus 40.
That'd be 3 times.
Oh, 6.
Very good. Didn't have to do that, totally depends on your comfort level with fractions. Coming up, doesn't change anything to multiply everything by 4. Okay,
Now we have to multiply the second
yep, and this gives us
term. 1x
squared, you go.
minus 14 root 3xy plus 7y squared. I'm gonna write that down so that's what I'm
Alright, Michelle's got that. Next one, this is fun. Who's got, wants to help me distribute this?
What is it?
Let me see.
6 root 3 times root 3.
Is that
Tyler,
18?
what do you think?
That will be that negative 18.
In this case, negative 18, Daryl, you're right, so it'll be minus 18 x squared. Root 3 times root 3 is just 3, times 6 is 18, plus,
18
or minus.
root
Minus
3. Minus 18 root 3xy.
Very good.
And
Minus- I mean, plus
well,
6
plus
root
6
3.
Here, actually, yeah, okay, I'll leave it like this. We should have taken a step and combined
Yeah,
3x plus
combine it.
3xy minus xy
Wait,
is
should we take a
2xy.
step back then?
No, let's, I don't want to erase anything, we'll just keep rolling with it and remind me to combine these in the next step, now it's starting to bother me. But that's going to be plus 6 root 3 xy, isn't it? Because negative times a negative. And then
Minus 8.
Is plus.
plus 18.
Oh, plus x.
Yep, but no, very good, plus 18y squared. Root 3 times root 3 is 3, times 6 is 18. Okay.
Plus 13x squared.
Uh-huh.
Square 26 root 3xy and 39y.
I should even try to get the
Plus 39y squared minus 64,
All equals 0.
all equal to 0. Let's start looking for like terms on this step. If no one objects.
Yes.
I'm going to underline the x squareds once. The xy's twice. And the y squareds I'll do 2 times, and I'll leave the constant terms, the one number, not underlined.
Wait, so is this gonna end up being an ellipse or?
I can't wait to find out. If the x squared and if the xy's disappear, the x squared and the y squareds wind up both being positive, then yes, it should be an ellipse. It better wind up to be an ellipse, parabola, or hyperbola
Wait, this is
though.
a weird question, but can we do like 21x squared minus 18x squared? Like, can we just write them all together?
If you'd like to see that step, I have no problem with that. Michelle's thinking this problem doesn't have any lines. At any rate, this is the unit where Parker had the brilliant idea last year to suggest that I come up with landscape oriented scratch paper for you guys. Because these lines go on for a while. I can give you some of that if you'd like, even for homework. Is that all the x squareds?
Yeah.
Yes.
Okay.
That amounts to 16x squared.
Excellent. Here's the important part. Minus 14 root 3xy minus 18 root 3xy, and then plus 26.
Oh, plus 6.
I got the plus
Oh, yeah,
6.
yeah,
Oh, but I didn't say it.
Yeah,
Here's the important part. In fact, I want to check this step before. I've never had to clear my ledge for room, except on this unit. Before I go any further, I really want to know if this equals 0.
Let's do math.
Negative
Negative.
32.
Negative 32, and then what's 6 and 2?
32 here.
Yes. On the first try, the xy's went away. Nicely done, guys. And then the y squareds are,
7y squared
thank you,
plus 18y squared
plus 18y squared.
plus 39y squared.
Excellent. And then I'm going to go ahead and say instead of minus 64 equals 0, I'm going to go ahead and say equals 64. Add the 64 to both sides. Let's pause a moment and reflect on this board. This is one of the smoother, shorter ones.
I'll move it to the
And then
chalkboard.
number 2
I
are
don't want the camera to follow over there.
-18.
So I'm gonna go back and erase that board in a sec. So before we get too far with that, Tyler, follow me back over here, please.
21
that
minus
happens,
18
doesn't
is 3 plus 13 is
16.
16 now.
16 x squared.
Race,
Hold
race,
on.
race, race.
5, 64.
Alright. So what are we getting?
16x squared.
Okay. Uh-huh.
Plus 64 y squared
Equals.
equals 64.
Okay, so here, when I divide everything by 64, I will get x squared over 4 plus y squared over 1 equals 1. That is, well, what is this? You guys tell me.
That is.
It is an ellipse. That's an ellipse. Where is the center?
The center is
0, 0, don't worry.
Excellent. Where are the, what does A equal?
A equals
That would
A equals 4.
2.
2 square root of 4.
Just kidding.
That's A squared.
And
What is,
B is 1.
equals 1, so we know that goes 2 units left and right,
yep.
and it goes 1 unit under.
What's C? How far am I foci from that?
C is, if I'm not mistaken, wait.
What's my formula
Is
for
it
it?
root 5?
C squared equals
Oh,
square
would-
root
it
B
would-
squared
root
minus
3.
B
Yeah,
squared.
minus B squared root 3, yeah. Daryl gave me what it would be on a hyperbola. But the foci are inside the ellipse, so this is
Right.
4 minus 1,
Root 3.
square root of 3.
Which is between 1 and 2.
Very good, sir. About 1.7. Yeah, it's between 1 and 2 because it's between, well, because it's between the square root of 1 and the square root of 4. I was blanking on that one. Yeah, if you do these right, I'm not going to have, I'm not going to give you like shifts and things like that on these. You're going to get a fairly simple shape if you do it right. So they should all be, on your test at least, they'll all be centered at the origin. But that went smoother and faster than a first try on this, I think, ever has. Nice job, guys. Previewing it yesterday was a good idea for a few minutes also, and you guys are good. Let's graph this thing. So as painful as it is to erase probably the neatest algebra I've ever done, which isn't saying much, I think, Tyler,
Why don't you just graph them?
I want more room. These have to be neater.
Oh no.
Okay, shall we?
Holy cow.
Now, if on the test I give you a ruler and we stick to 30, 45, and 60 degree angles, since I always give this test without a calculator, how can you draw a nice 30, 60, or 45 degree angle for me on graph paper? Start thinking about that for a second. I don't give you a protractor or anything else. Any ideas?
I mean, for a 45 degree angle, you can just do 1 over and 1 up.
Bingo. Make sure the slope is 1 and you've got a 45 degree angle. Go to any XY point where they're the same. What about a 30 degree angle?
You can do,
Nope.
What do you know about a 30, 60, 90 triangle?
It
that
is
is like
1, 2,
for a
or 3.
30, yeah, no, it's, across it is 1, then
1, 2, root
1, root 3, and 2. I like to go legs, then hypotenuse there, but you got the right numbers. See, this thing I'm not going to have to go past 1 or 2. Okay, so my scale can be,
Pretty big.
yeah, just 1, 2, that'll work. 1, 2. Now this is where your book uses the x prime and y prime for your new axes. As I mentioned yesterday, you don't really think in terms of rotating the conics. Although I find that an easier way to explain it at first. You're supposed to actually think in terms of rotating. You're not supposed to think in terms of rotating the ellipse, you're supposed to think in terms of rotating the axes. But It's a little bit rough to do, but if I want a 30-degree angle, and if I have a ruler, I can do this more carefully. If I go up 1, how long should my hypotenuse be?
Go up 1, your hypotenuse should be root 3.
Root 3 should be your adjacent.
Oh, so 2.
Yeah, if I want a 30-degree angle, if I go up 1, if I want a height of 1, I should have a length of 2. The ancient Greeks could do all sorts of crazy things. One thing they would do, you know that compass, not the one that says north, south, east, west, but the one that lets you draw nice circles?
And then they get
Yeah. Put that here and rotate it up until you're as high as the 1.
Wait, so do you go over 2 on
Oh no, you don't, well, if you go over 2 with a ruler, or if you go over 2 with a compass, then you go up until you're the same height as 1, and then you know you've maintained a length of 2.
Wait, are you going to be giving us a compass for the test?
Maybe. Do a little construction.
So like this then?
Yeah, as long as you're sure, if that's your length of 2, okay, and you go up until you're at the same height as 1, which you've done with the line on your paper, yeah, that's 30 degrees. Certainly closer than I'm going to double check. So that's a good way to do a 30-degree angle. Michelle actually has a ruler in her hand, so it's neater than that.
But where's that point?
This point, this would actually be the point square root of 3, 1.
Oh, okay.
If I've really made a 30-degree angle. But I'm not too worried about that. Now, on this axis is where you graph your ellipse. Now, I'm not going to be super careful, but I take that back. I'm going to be super careful. I'm going to give you rulers and ask you to be super careful. But I'm not going to pull out a protractor and a laser level and a couple other things and triple check that you did this perfectly. Okay? But I expect you to put some real effort and a little geometric thought into drawing these new axes.
Wait, so that one should also be like a 30.
This should also be a 30-degree angle, yes, so this should be the point -1, and it should hit at root 3, about 1.7 on the y-axis. Now, our ellipse. Is this ellipse, if this weren't rotated, would this ellipse be along the x-axis or along the y-axis? Would it be larger, would its major axis be along it?
It'd be larger along the axis.
Larger along the x-axis, would be horizontally stretched. And in fact, from the origin, we would go out 2 units. I figure from 2, do this with green. So from the 2, if I were to go up in a nice circle, that would be where my ellipse would end. From the -2, if I were to have a point of my compass at the origin, go down to there, that would be my other end of my ellipse. How high up and down would this ellipse go if it weren't rotating? 1 unit, thanks to that b squared over there. So, if I took my compass from, say, -1 on the y-axis, +1 on the y-axis, and rotated out, that would be a nice way to find where the points 1 and -1 and -2 and +2 are on my new axes, which your book calls the x prime, y prime axes. Your book will also call that ellipse as x prime squared plus y prime squared. I've tried that a few years, but watching you guys try to do that long algebra with all those primes in it, most kids get messy. My foci are root 3, which is about 1.7. So go to about 1.7. And of course they're along the major axis of the ellipse. And try and make a nice circle down, and that's where the foci are. And it's exciting. Notice I'm taking a little more time than I usually do, and it's still probably not going to be all that pretty. It's very Christmassy. And it looks like a slightly deflated football. I'll bet you money Michelle's is better. Actually on her desk. So here I have my vertices. I'll label my foci. I won't ask you to label where these 4 points are on the standard coordinate plane. I mean, it's on the new x prime axis, this is the point 2, 0, and this is negative 2, 0, and this is, what is this? 0, negative 1, and that's 0, 1. How do you think you could find these points, just out of curiosity? Maybe that'll be extra credit on the test. How could you find these points?
You'd plug them back into our x equals x cos theta minus y sin theta.
Give me those again. So x equals
X equals x cos theta minus y sin theta, and y equals x sin theta plus y cos theta.
Well, if it's that easy for you guys to figure out. So 2, 0 then would become, let's see, the new x coordinate would be 2 times cosine 30 degrees minus 0 times sine 30 degrees, which is, that's root 3 over 2, double it, that's just root 3. And my new y would be, well, 0 sine 30 degrees. Wait, that doesn't make sense. Ah, no. I gotta use the x, sorry. 2 sine 30 degrees plus 0 cosine 30 degrees.
1.
1. So this is the, go back to blue, because that's what I did my rectangular axis in. So this is the, on the blue axis, this is the point.
But we won't have to say it on the blue axis, right?
I'm seeing a really good extra credit opportunity. Now from here you can also use, there is symmetry at this point. So if this is root 3, 1, what do you think this point down here is? Negative root 3, negative 1. And the up and down points are actually going to be similar triangles. If you don't like using this, you can also use geometry. That's a hypotenuse of 1, that's a 30-degree angle. What's the short leg going to be? What's the long leg going to be with a little bit of geometry? Well, it's on the unit circle also. This is also, if it's a radius of 1, that's 120 degrees on the unit circle, which is negative 1/2, positive root 3 over 2. Very good. And then down here, that would be, on the blue axis, waiting for Michelle to save me here, but
1/2.
negative root 3 over 2. There you go. That's definitely extra credit on the test. If I had more time, if I could give this test in like an hour and a half period or something, that would make it part of it. But yeah, like Joey said, if you don't like the geometry, plug the actual points into these formulas, your new x
We
form.
get this on our test.
I'm still thinking. If you got that on your test, it'd be too easy.
Oh my god, no, it would not.
Plus they're not all going to line up with 1, you're going to have to double it and do proportions.
So then, it's fine.
Maybe. Tell you what, if you got that, this would not be extra credit.
Okay.
If you got the unit circle, this would be.
Then I can tell you.
You like that idea? Jen is going to watch this over the weekend and scream at you at her computer screen. I'll think about that. We'll talk about that. I'm open to negotiation on that one. So that is your first rotated conic. Is it guaranteed? Will it always be an ellipse? No. Ellipses, hyperbolas, parabolas. One particularly cruel thing, I didn't scan your homework.
How do we do another one? That's not an ellipse.
Well, you got to remember everything about that you did about ellipses, hyperbolas, and parabolas before. You've got to be able to draw ellipses, hyperbolas, and parabolas as well as you did on the last test on these green axes. Okay? They're all going to be centered at the origin, and they're, it's perfectly alright to shift them. For shifting and rotating them though, actually that's where parametric form comes in handy. Because, debating if I tell you this now, if this ellipse were in parametric form, let's see, this ellipse in parametric form would be just x equals 2 cosine t, y equals 1 sine t, correct? H and k are both 0, and this is the length of the semi-major and semi-minor axis. That's your A and your B, parametrically. In this case, t is the angle, and if you want to rotate an ellipse parametrically, all you have to do is add or subtract at the angle.
Like, this is a really stupid question, but going back to like what we did in the beginning when we were able to plug in arbitrary values of like x,
Yeah,
theta,
polar coordinates.
yeah.
Can we shift this to polar?
Yeah.
You can do a polar ellipse, we're gonna do that, and then we'll do polar form of ellipse after this test, I think, but once we do that, in polar form or in parametric form, you can actually just add or subtract to the angle, and that will cause the rotation. But polar conics are not quite as simple as this. If I have to rotate a conic, I'm gonna go parametric personally. This can get messy though, in other ways. I want to do one more of the. I want to start one more of these and just do the algebra part, not graph it. And it's my favorite one that I think we'll have just enough time for. Quick questions on this, including how we use these formulas to get these points. Nope. Okay, Tyler, follow me back over here, please. We're going to do something you may have seen before, but probably not in this form. Believe it or not, this is a rotated conic. If you look at your general form of a rotated conic, ax squared plus bxy plus cy squared plus dx plus ey plus f equals 0, this is xy minus 1 equals 0. A, C, D, and E all equal 0. Now normally if A and E equals 0 you wouldn't be looking at a conic, but remember that's the rule I gave you for when they're not rotated. Once they're rotated, all those rules about how if A and C are both positive it's an ellipse, and if one's negative it's a hyperbola, and if one's missing it's a parabola. The
They're all
rotation,
gone.
yeah, they're all gone.
It's
There are-
fair game.
There are other rules. There are other rules, which we may go over, but I prefer to just go through the process and see for now. Make you wonder and guess, predict. This is actually the easiest one to unrotate, as it were. Well, first off, we have to know what the angle is. So, what we have is tangent to theta equals b over a minus c. Well, what's b in this case?
1. This is 1.
And what's a minus c?
0.
Yeah, 0 minus 0.
Wait a minute.
So we have something undefined. Now, when is the tangent undefined?
When
the
1 over
it's
0.
at 90
one
degrees.
is
90 degrees, which is when cosine is 0, which is, yep, y'all have the right idea. So this happens at 90 degrees, so if 2 theta equals,
Theta equals
90
45.
degrees. then theta is 45 degrees, very good. So in this case, when we go to our x equals x cos theta minus y sine theta, and y equals,
X sine theta plus
Thank
y
you.
equals theta.
very good, plus y cos theta. I'm going to do that step here with a marker that isn't dying on me. And this is going to
Every class
become,
would lose a marker.
pardon?
Every class would lose a marker.
It seems like. Well, I do share these, and I do run them back and forth from physics downstairs some days. So, root 2 over 2x. The advantage of 45 degrees is sine and cosine are both root 2 over 2. So that's what we get. Now we take our substitution formulas here, plug them in for x and y back in the original. So this becomes root 2 over 2x minus root 2 over 2y times root 2 over 2x plus root 2 over 2y. And again, if you remember your factoring patterns, if you remember that A minus B times A plus B equals A squared minus B squared, oh, I'm sorry, this equals 1. If you remember this factoring pattern, then this goes fairly quickly to, follow me over here again, Tyler. Change my mind, I will need this board. Okay, so this goes to root 2 over 2 squared is
1/2 x squared.
one, isn't it? Yeah, 2/4, 1/2. Very good. So that goes to 1/2 x squared minus 1/2 y squared equals 1, which I'm going to rewrite as x squared over 2 minus y squared over 2 equals 1. So what are we looking at there? We've seen it before, but not quite this.
It's a hyperbola.
It's a hyperbola, yes. Keep the inflection neutral at the end, Joey. Shows more confidence. It's a hyperbola.
Hyperbola.
That's right. There you go. This is a hyperbola where A equals square root of 2, B also equals the square root of 2. And in this case, with a hyperbola, we have c squared equals a squared plus b squared. So c squared will equal 2 plus 2.
Which is
So
4.
c equals
4
2.
squared is 2.
Square root of 4 is 2.
I mean, yes.
Right idea. I'm going to graph this one quickly. That went a little faster than I thought. And hopefully not too fast for Jen and Noah. Now, I don't need much room on this. Yes? Someone's going to say something?
I'm just thinking no one's here. This is easy.
Maybe you would.
Jim would blow up.
Alright, so here's my 1 and 2. -1, -2.
-1, 1.
I'm writing the negatives on that side. Okay. My rotated axes are at a 45-degree angle. This one, if you got a ruler, I expect to see a nice 45-degree new axis going right through the point 1, 1, right through the point -1, 1, right through -1, 1, and right through 1, -1. Not quite holding myself to that same standard on this board right now. Okay, so now I need to make my box. Remember, for hyperbola, we draw the box and we draw the asymptotes. The box is root 2 and up and root 2 down and root 2 right and root 2 left. So how can I find the square root of 2 quickly on my green axes?
Well, you know, it's like between 1 and 0 and 1. No.
It's between 1 and 2, it's about 1.4. But let's think geometrically for a minute. Where's the square root of 2 sound familiar?
Oh, it's like up 45. The 45, it's at the top. It's a tangent.
So you go back to the unit. You love that unit circle. I love this.
1 for 2.
So, but Tyler, I'm going to go with Tyler's geometry memory here for a moment. If you have an isosceles right triangle, two 45-degree angles, root 2 is the hypotenuse, both legs will be 1. So if I go to the point 1, 1, I happen to know that I am root 2 units from the origin. So if I go to the point -1, 1, -1, -1, and 1, -1, I'm going to find myself root 2 units from the origin and yeah, I really did a horrible job of drawing this. I apologize.
It's because the scale
Okay,
of
this
the.
is going to be a really weird question.
Yeah.
Now, how do we know which side is the
Hold on. I don't think it's a weird question at all. Now, if you draw this right, I think I'm about to answer your question as I attempt to salvage my horrible scaling job after I was just telling you guys how I expect you to do it neatly. Again, my original plan was to do this with technology, but I couldn't get the room dark enough to use the projector. Okay. You draw your box and we're doing a hyperbola. I just drew my box wrong. I completely drew this box wrong. I love that I did that on tape. That's fantastic. When you go off I was doing something else. When you do your A and your B on your hyperbola, those are the midpoints of the sides of your rectangle, remember? Those are not where the corners are. When we went B units over,
Oh, the corners are big. Right.
Oh, yeah, we did it on the
Yeah.
normal copy.
smooth.
I might as well just fold my piece of paper upside right to this side.
At an angle. Kids have asked me if they could turn that in. Can I just graph it and then can't you just grade it at a 30-degree angle? I have said no.
No, but it's true, like, if we were to do that.
And then we tell you like,
Shouldn't have said
look at
anything.
my paper at a 30-degree angle.
That's right, sure, no problem. By which I mean, no.
Or I could have my paper at a 30-degree
All right.
angle.
Okay, now what happens here if you draw this very carefully is with a 45-degree rotation, your corners of the box we always draw for hyperbola will actually hit the original x and y axis, the non-rotated x and y axis. So those are the asymptotes of your rotated hyperbola. The vertices are here at where the box hits the transverse axis, the one that cuts across. I haven't even mentioned this, I've been presuming you guys remember. The x term is positive, so if this weren't rotated, it would go through the x-axis. Since it is rotated, the wings of my hyperbola are cut by the x prime rotated axis, instead of my wings being cut by the x-axis. So the actual hyperbola then uses the original y-axis and the original x-axis as its asymptotes.
But how do you know it doesn't go back down?
Here's my x prime axis, right? Okay? X is positive and y is negative. That's how we knew which way it went before.
Oh, yeah, just forget I just said that.
Okay, God, that was a whole test ago, Michelle. Easy to forget. And my foci, let's see. That's a distance of root 2. That's a distance of root 2. This part's easy. My vertices, I'm forgetting the colors I use. My vertices on the green x prime axis, the vertices of the hyperbola are root 2, 0, and negative root 2, 0. But if we were using the blue axis as our orientation, this would be the point 1, 1, and negative 1, negative 1.
Oh my god.
So on the green axis, it's root 2, 0, negative root 2, 0. On the blue axis, if we're going by our unrotated orientation, would be the point 1, 1, negative 1, negative 1.
And then that would be,
That's how we draw a box.
negative, that would be negative 1.
Positive 1,
And then
or just 0, root 2 on the green. That's for finding, yeah, where those boxes are. Put those in for fun. So this would be 0, root 2 on the y prime axis, and 0, negative root 2 on the negative y prime axis. But if you're going by the original unrotated xy axis, this would be 1, negative 1. This would be negative 1, 1. The foci are going to be along the x prime axis, 2 units along the x prime axis. There's a couple ways you find this. You could take a compass from here and rotate it up 45 degrees